So welcome to lecture 6B of CS 302 data structures. So in the last lecture, we have seen the insertion algorithm in case of array and linked list. And in this lecture, we are going to see the deletion algorithm in case of array and linked list. So like the insertion algorithm, deletion can also happen at the beginning of an array or linked list, can happen at the end of an array or linked list, or it can happen at the middle, like after or before a given value or after a given number of nodes. Let us first check it for the array. What will be the complex, how we are going to delete an element, and also what will be the complexity of that. So first let us see the deletion at the beginning of an array. What happens is that we have a given, suppose we have a given array like that of 5 element size. So the size of this array is, let us assume it is of int int a5, suppose, and let the elements be like this. So the elements maybe are like this, 10. So we are not considering whether it is sorted array or unsorted array, it doesn't matter. Suppose my elements are like this. So at the beginning of the array means we have to always delete the element at the index 0. Now what happens? In case of an array, if we are deleting, that means this memory space have to be overwritten by some other value. So if it is overwritten some other value, then we can assume that that value has been deleted. Now if it has to be overwritten, what we can do, we have to shift all the elements which is on the right hand side of this index 10 to the left. So all the elements on the right hand side of the index 0 will be shifted to the left. And once that is done, what happens? We get a new array like this. So again there will be, so this is in case of a static array. So index remains same, no change in indices. But what happens is that the element which were on the right hand side now gets started from index 0. So it becomes 40, this becomes 30, and this becomes 20. You see that there is no change in the size of the array. The size remains A5. The only thing is that the element on the index 0 has been removed and occupied by the element starting from index 1. Now we see that if we have to delete, deletion requires shifting, like in case of insertion, it requires shifting of the elements to the right. So if my array is of size n, then n-1 shifts are required. If the whole array, so if there are 5 elements in this array, then I require at least 4 shifts. So I can write that if the array is full, that is consists of n number of elements, then in the worst case, n-1 shifts are required. In the worst case, n-1 shifts are required. So we can see that in the worst case, because of the shifting operation, the complexity of array deletion will be order of n. So we can safely write that complexity will be order of n in case of deletion in an array at the beginning of the array. Now let us see the next one, that is at the end. So what happens if we want to delete an element at the end of the array? Now let us see this particular example, the same example which we have used in the last case. Now see what happens, we want to delete at the end, that means we want to delete this particular element 20. What happens? We are not doing any kind of shifting operation. So we are basically searching the whole list and reaching the last index and simply deleting that. Deleting means we are simply emptying that location. Overwriting it with some zero or something. That means that space is not there. Now this deletion algorithm doesn't require any kind of shifting operation. So the complexity in this case, is simply search time, because we have to reach the end of the list, plus order of 1. Because we are just reaching the place and we are deleting that element. Deleting means we are simply overwriting space. We can also shrink and expand the list, but that is a different issue. We are not going into it. So it is order of 1. Deletion at the end, like the insertion part. Now let us see what happens if we are doing at the middle of the list. So let us consider the same thing and let us assume that we are going to delete it after a given value. And let that value which we want to, after which we want to delete be 40. That means we want to delete the value 30. This value 30 we want to delete at the middle of the list. So let this value be 30. So what we have to do, we have to start from the beginning of the list, search for that particular element 30, so we reach this place. Once we reach this place, what we have to do, we have to delete this space. Delete means again shifting all the elements which are on the right hand side of 30 to start from the index 2. So 30 was at index 2. So we have to shift all the elements starting from the index 3 to start from 2. So the scenario will be like this. So 10, 40, 20 and the remaining space will be unoccupied. So again you see that when we delete an element at the middle of the array, what is required is a shifting operation. And we have seen that shifting operation in the worst case takes order of n time. So again, the complexity can be thought in this case to be, because we have to search for the element. So searching again can be deletion at the middle of, so deletion at the end can be thought of like a special case of the deletion at the middle. So suppose we want to delete the value 20. So we don't know where is it. So eventually it may become at the end of the list. So in the worst case, the complexity will be equals to the search time, searching for the particular element after which we want to delete, and plus order of n, which is for the shifting operation. So anyway, for array, if we see the deletion at the worst case is order of n complexity. Now let us see what is going to happen if we are taking it for a linked list. So in case of a linked list, if we want to delete an node at the, so in case of a linked list, if we want to delete a node at the beginning of the list, see, like in case of insertion algorithm, we were checking whether Avel has any memory space left to be allocated to a new node or not. That is, we are checking for the overflow condition. In case of a deletion, we have to check for the underflow condition. What is meant by underflow condition? It may happen that the pointer start is pointing to nothing. That is, the list is empty. So if the list is empty, we cannot delete anything from the list. So at that point, it will be reporting me an underflow condition. So that means the list is empty, there is nothing to be deleted. Now this step is common for all the deletion algorithms. Next, what we have to do, now let us assume that our list is not empty. So this list is not empty, but it has certain number of nodes. So let me draw two nodes. So one is this node. The other is suppose 5. And let us assume that the address is 200 and this address is some 100. So this is the last node. It will have no next pointer path. And here the address 100 will be there. Now, what will be the input and output for any kind of deletion algorithm? So the input, so any kind of deletion algorithm, the input will be the given list and the output will be the new list. Because after the given value has been deleted, so the output will be the new list. Now what we are checking, so we are first setting a pointer to PTR start. That means, so here also it is 200. So at first we are setting a pointer to this node. We are deleting at the beginning of the list. At the beginning of the list means we want to always delete the first node. So we are setting a pointer to this node. Now if we want to delete this node, what will happen? This node will become the first node in the list. So 200, so start is pointing to this node. If we want to make this node to be the first node, we can get this address from the start arrow next part. So this is pointing to this node means in the start arrow next part, we get the address of the next node in the list. So that's why what is done, start equals to start arrow next. So if start is made to start arrow next, that means start is made to point to this node. So what is there in start arrow next? In start arrow next, it is 100. So again, let me write down for your convenience. So in start, it is 200. PTR also contains 200, but PTR arrow next or start arrow next is equals to 400. That you can check from here. Is 100. And 100 means so start. So if I write start equals to start arrow next, that means I want to point it to 100. So that's why this link. Once I do this, what I can do, I can free PTR. Now what is meant by this particular line, free PTR? See, I told that linked list is generally implemented in the form of dynamic memory allocation, that is using malloc and calloc. And whenever we are allocating memory space for something using dynamic memory functions, malloc and calloc, we have to free that memory space after my program is over. So free is basically that free function which we use for dynamic memory allocation, that is a free. So basically it is free PTR. So when I show you the implementation of this algorithm, I will be showing you at that part how to do that. So once we do this, then I can delete this node. So free PTR means this node we can safely delete. So what is the complexity? You can very well see that in this case, the complexity is equals to order of 1 because we are doing some pointer operations which take constant time. And therefore, the linked list deletion of the first node or at the beginning is a constant time operation. Now let us see the deletion algorithm in case of a linked list at the end of the list, that is at the last node. So again, the first step is common, that is checking whether the start node is null or not. That means whether the list is empty or not. If it is not so, then deletion at the end requires us to go till the last of the list. So again, we set a pointer to the first node. So we set a pointer to the first node and we have to reach the last node. And like insertion at the middle, we were using 2 pointers, holding the 2 points between which we have to insert the data. Similarly, in case of deletion of the last node, what we have to do is that we have to use 2 pointers. Those 2 pointers are going to hold to the one which has to be deleted and the one which will be just before the last node, respectively. So let us see. So what we are doing, we are making PTR equals to start. Now we have to go till the last node. So PTR arrow next is not equals to null. If it is not equals to null, what we do here, we set another pointer which is PPTR. And we make PTR point to the next node. So PTR was initially pointing here. Then we are checking for the next pointer part of a node. If it is not null, then we set another pointer PPTR to this node, current node, and take PTR to the next node. So PTR is taken to the next node. So now what happens? Again, we are checking whether PTR arrow next is equal to null. Now, yes, it is equals to null. So we stop. So you see that PTR is pointing to the node which has to be deleted. Well, PPTR is pointing to the node before the last node. Now this node is going to become the new, so this node is going to become the new last node. Well, this is the node to be deleted. So once we do that, what we have to do, so in the PPTR arrow next we put null, because now this is the new last node. So we know that in the last part of a linked list node, it is always a null. And we simply free this. So free PTR. So in this way, we can delete the last node in a linked list. In this case also, you see that the complexity consists of 2 parts. So the complexity is equal to search time. Search time in the sense, we can, instead of writing a search time, we can write traversal time, because we are traversing till the end of the list. And the deletion is a constant time which is order of 1, because this is a few pointers change. Next, let us check the algorithm for deletion at the middle of the list. So now let us see this example where I have taken 3 nodes. So the input to this program will be the list and the value after which we want to delete. So that is the value num, and the output will be the new list. Let my value after which I want to delete be 10. So after the given value node 10, I want to delete the node. So the first is checking for the null condition. Then, like the insertion algorithm, I make use of 2 pointers. So one is PTR equals to start and another is PPTR equals to PTR. So what is there in start? So my start is equals to 200. So PTR also is equals to 200. And pre-PTR, let me write in short, PPTR is also equals to 200. So all my pointers are pointing to this part. So this is where PTR is also there. And this is where PPTR is also there. So both my pointers are standing here right now. Now I have to check whether I have reached the data part equal to num or not. So what I'm going to do, like the insertion, PPTR arrow data is equals to num or not. So here in this case, so let this value be 5. So then it will be better, we can make use of. So is PTR, PPTR arrow data equals to num? No. So what happens? We go inside. We make pre-PTR equals to PTR. So let me write down here. So PPTR equals to PTR means it is equals to 200. PTR is equals to PTR arrow next. That means it is equals to what is there in the next part of PTR is 400. So now what happens? PPTR remains here because it is equals to 200. But PTR moves to this part. Okay. This part I will just, there is a small mistake here. It is not 400, but it is 100. So this part is 100. So PTR will move to this node. Now, is PTR arrow data, PPTR arrow data equals to num? No, it is not equal. So again, what happens? PTR address is assigned to PPTR, so which is 100. So again, let me write down that. So PPTR equals to PTR equals to 100 and PTR equals to PTR arrow next, which is equals to 400. So PTR moves forward. So what happens? PPTR is moved from here and PPTR comes here and PTR moves to this node. Which node do we have to delete? This, the node which is pointed to by PTR, we have to remove. So again, is PPTR arrow data equals to num? Yes. So we stop, we come out. Now we make use of another pointer which is temp. So temp is assigned to PTR. That means temp also points to this node. So temp is also pointing to this node. What we have to do? PPTR arrow next is equals to PTR arrow next. So whatever is there in the next part of PTR, we have to copy that to the PPTR arrow next. So what is there in the PTR arrow next part? None. So we remove 400 and that is overwritten with none. So once this is done, we can free temp. So this part can be deleted. Here you can either free temp or you can also delete PTR. You can try it out on your own to check whether if we don't make use of another pointer, what is going to be the consequence. Now remember, linked list algorithms can be written in multiple ways, but the basic steps remains the same. You can try out the different types if possible by you, and in case of any difficulty, you can contact me. Now, what will be the complexity in this case? It will be same like in case of deletion at the end. So there will be a complexity of search time. So basically we are going to search first. Like in case of deletion at the end. So we can think of it like complexity equals to search time. Search time here is for the element which we are going to, after which we are going to delete, and it is order of 1. So search time plus order of 1, because again deletion is a few pointers change. So we have seen the algorithms for deletion, how to delete an element from a array, and also how to delete a node from a given linked list. Now let us check the complexity comparison of array and linked list. So we have seen the following operations. So in case of access, we can tell that in case of access, we have seen that in case of array, we can access any element by indices. So the access time is order of 1. While in case of linked list, we have to traverse the whole list. So it will be order of n. Searching for a particular element in an array, we have to traverse the whole list. So it is order of n, and in case of linked list also it is order of n. In case of insertion, if we have to insert an element in the array, we are traversing the whole list. So this is order of n time. While in case of linked list, the best case is order of 1 because that is at the beginning of the list. Similarly, deletion also order of n because we have to traverse the whole array to delete an element. While in case of linked list, it is order of 1. Now, what is the space complexity? Space complexity means, as I told, what will be the space taken by each of the data structure when we are implementing it. So, if you are having an n element array, or if you are want to insert n number of nodes in the linked list, so the total number of spaces which will be reserved for both array and linked list will be n. Naturally, because we are doing it for n number of nodes and n number of memory, n number of continuous memory spaces will be reserved for array, while n number of non-continuous memory spaces will be reserved for linked list. So in both the cases, it is ordered of. So in the next lecture, we will be seeing some usage of array and linked list in practical life, namely how to represent a sparse matrix and polynomials using both array and linked list. And I will be describing you the algorithm for inserting a node after a given value. Thank you very much.